Okay. Oh.
Okay, thank you everyone for joining us again. So our first speaker for this last session is Shishir Patil. He'll tell us about Gorilla connecting LLMs with massive APIs.
So good evening, everyone. So I'm Shishir, and today I'll be talking about Gorilla. And the goal of this talk is to address two what I think are critical questions that most of us might have today, which is when do you fine-tune an LLM and when do you use retrieval? But second and more interesting to this audience is how do you measure hallucination, which I think are two of the open and interesting questions in the LLM space today. So as a quick introduction, I'm a PhD student at Berkeley, where I collaborate with the Berkeley AI Research and the Skylabs. So a lot of my work is at the intersection of systems and machine learning, and that kind of informs and inspires some of the work that I'll show today. So let's take a look at the world today, right? The way you interact with LLMs today is that you have one too many LLMs. You as a user is going to ask an LLM for a prompt, get a response, and you might do this multiple times. And then the burden lies on you as to what you do next with the response that you get from the LLM. You might then go ahead and then use the response that you have to bring about some effects in the rest of the world. This could be in terms of writing some proofs in your LaTeX, or copy and pasting the command to execute it in your terminal, so on and so forth. But basically, the burden of this act and response lies on you. There are some toolings like LangChain, MinGPT, etc., that some of you who try to practice LLMs might have used it. But fundamentally, you're at the center of the LLM world. Now, in our view, what we really want to do is flip both of this. So you as a user is going to introduce a prompt to the LLM, and this could be an intent of what you want to do. And now the LLM is going to go and act on the rest of the world. This could be either in terms of just reading the states or even performing some actions that's going to change the state of the world. And then you get your feedback from the world, which your LLM is going to handle, and then return back to you. And you may just choose to accept what's happened, redo what's happening, or even cancel what you just did. But fundamentally, the goal is, can you replace the human at the center of it to make the human, in some sense, just interact with the LLM that now interacts with the rest of the world? So that's the vision and that's the desire. And that's where, to ground this in a concrete example, many of you might have tried to train, fine-tune, or even play around with LLMs, and we know that GPUs is a scarce resource, right? So suppose you say, I want 800 GPUs in East US, and that's what you want to do. Now, what we want is an LLM, and in this case, Gorilla, which is an LLM that we have trained at UC Berkeley, that then goes ahead and then sees if this, in East US, is there capacity for an 800 GPU. If so, returns it to you. And if not, it returns and says, hey, I might have West US instead of East US. And you get the response, and then you can now introduce effects into the world. So this is the high-level idea, where instead of having you talk to the LLM and then get the response and then perform some action on the rest of the world, can you just talk to the LLM, and now the LLM is going to perform an action on the rest of the world. So that's the goal here. And so today, when I say talk to the world, what does that mean, right? So the way we think about LLM is as a tool, and tools need to talk to each other. In computer science, the way tools talk to each other is through well-defined API calls. And so that's what we are targeting. We are trying to teach an LLM how do you write and invoke API calls such that you can now bring about these effects in the rest of the world. And to start off with, we have some very popular APIs. But rather than just talk about it, let me show you a quick demo. And by the way, all of this is open sourced, and you can access it as well. So here, there's a small box in Berkeley that I'm connecting to. And the user prompt is simple. I want to translate from English to Chinese. Oh, sorry. So yeah, so here's, you just connect to the Berkeley instance. And then if you were to say, I would like to translate from English to Chinese. Now, this is not something that an LLM can now do today. Like if you ask this to ChatGPT or any of your open source LLMs, it can probably spit out something. But the whole point is you are dealing with what the LLM knows, and there's no way for it to grow the information. You're fundamentally restricted with what is in your pre-training set. Instead, if I were to teach the LLM how to call the API, in this case, I'm going to use The screen is not very clear, but I'm going to go ahead and call this API, which is pipeline translation English to ZH, Chinese, and then I'm going to spit out a bunch of code as well. So what you can do is you can just deploy this code. This is just a subprocess.p open, or go ahead and execute this code, and what you'll see at the end is actually the end result, right? So this is just a toy example in the interest of time, but the way we are able to do this is fundamentally because of our training recipe, and to enable this, we had to address two important questions. And right now, I'm going to slightly switch gears and talk about how we address the two, what we think are interesting and fundamentally open questions today. So the first question is, how do you mix fine-tuning and retrieval, right? Fine-tuning is where you take your pre-trained LLM, you may call it the foundation models or frontier models, and then how do you now, this includes, I know some of you mentioned about RLHF, instruct tuning, et cetera, to then fine-tune it for a particular task or fine-tune it for a particular goal as such. What we knew, or at least for the hypothesis, what we wish were true, was that in fine-tuning, you're augmenting the behavior of the model, whereas you use retrieval to introduce new knowledge into the model. Now, what we demonstrate with Gorilla is that this is not very true. Fine-tuning is, in fact, remarkably effective at both incorporating behavior and knowledge, except retrievers are inaccurate, right? So today you have billion-scale vector databases and multiple ways of doing similarity search, maybe even dot product or cross product, but retrievers are fundamentally not accurate, right? Even the best of the class retrievers give you about 70% accuracy. In other words, you're wrong 1/3 of the time. And if you were to give a wrong information to a model and ask it to say, can you now answer the question, garbage in, garbage out, right? So how do you overcome this? So to answer this, we introduce something called RAT, that's retrieval-aware training. So the idea is simple. We're going to fine-tune the model and teach it to either use or ignore the retrieved context, right? So during the training process, I'm going to give the model examples of correct and incorrect information and ask it to make this one bit high-level decision. Is this the correct retrieved context or is this the wrong retrieved context? And if it is correct, then you go ahead and you use that. And if it is wrong, then you discard it and use your knowledge from your pre-training set, right? So let's go with an example. This is a pretty busy slide, but I can walk you through it. So the user prompt here is, I'm an engineer at Uber, and I need to find an API that can classify pedestrians, cars, etc., from an image of the scene. So now most of you might know that this is just a classic image classification task, right, or object detection. Now I used a retriever, and this could be your favorite retriever that you can use. And the retriever said, hey, here's a reference API. Why don't you use this reference API to answer this question? So the first thing that we teach them all to do is answer this question, is this relevant? In this case, I'm doing object detection for an API that requires classifying pedestrians, cars, etc. So this is probably correct. That's what the model learns. And so then the model goes ahead and gives you the response as to what you need to do, and also an explanation to make it slightly more interpretable. But in the other scenario, where the user asks, I'm an engineer at Uber, and I need to find an API that can classify pedestrians. If you can see over here, what I really call is a PyTorch fair sequence, which is really a translation API. So in this scenario, if you were to call a natural language translation API to do a classification task, then the Gorilla model learns that this is actually irrelevant. So you need to discard this information over here and just rely upon your historical information that you had during pre-training to go ahead and answer the question, right? I'm happy to take more questions at the end, but this is what we think is pretty critical, especially as you go ahead and you start augmenting your models, even with longer context lengths, is that you need a way to figure out if your retrievers were accurate or inaccurate. And if they were inaccurate, how do you account for it? Now, that brings me to the second part of the talk. And to start off this talk, let me ask a simple question. How much does GPT-4 hallucinate? Right? I see some heads nodding, but a lot of the times the responses you get is like a lot, a little, maybe, or compared with some other model. But it's basically adjectives. There's no way where you can accurately put a number to measure how much does GPT-4 hallucinate.
Doesn't it need a distribution of the prompts?
True. If I were to give you a distribution of the prompt, then would you, sorry?
So you measure the accuracy, how sure are you to define accuracy, whether you think you can do the retrieval with that or not? And what is accuracy of measure accuracy?
Yeah, so that's a great question. I think once I answer this, that might help answer some of that.
But technically, every output that LLM produces
is the same process. It's always hallucinating. It just happens that sometimes the output is factually correct and sometimes it's not.
Right. So how do you measure that?
That is your problem.
Yes. So I'm going to answer that question today. And one benefit we have is by using APIs, I'm going to pull out a simple trick that people use in programming languages before, which is abstract syntax tree matching. So how does this work? Like you said, the LLM is going to produce an output. In this case, the API we decide to call is torch hub load PyTorch vision densenet 1-to-1 pre-trained equals true. So this is an API. So here I'm giving examples of machine learning, mostly because we're trying to write a paper and for the community this works well. But you might think of this as being RESTful API calls. Great, okay. So I'm going to slightly speed up because I've been told I don't have a bunch of time. But the first thing we do is build a small syntax tree from this. And then I ask a simple question. APIs are extremely deterministic. So that's a benefit that we get from the domain. So I can build an AST, not a subtree, but an entire tree from my data set. And I'm going to ask a simple question, is there a proper subtree match? If there is a proper subtree match, then this may or may not be accurate, to your point, but at least it's not hallucinated. So for Uber, if I want to give a translation, it's not hallucinated. That exists. It may be the wrong task. So the accuracy may be bad, but at least it's not hallucinated. So I'm going to do this, and I don't know if the color is accurate, but here I see that, OK, this is actually a fair match. And you see that I haven't really checked for pre-trained equals true because that's an optional argument in Python. So then I'm going to do this subtree match and then tell you that, OK, this is not really hallucinated. And this is, of course, a cherry-picked example where I show you that we can do well. GPT-4 tends to hallucinate. Cloud may be wrong. But how does this perform across an actual data set, right, beyond these examples? What I have here is hallucination on the x-axis, accuracy on the y-axis. You want to be in the top left corner. Lower hallucination is better, higher accuracy is better. And as you can see, Gorilla can do much better than a lot of closed source and open source models. And not just that, even with the best retriever, what if God gave you a good retriever, which is the Oracle retriever? We're never going to get here. This is the state of the art, by the way. But even in this scenario, you can see that with our recipe of training, you can actually do better, if not as good as a closed source model. Okay, so this is not just an academic project. We are trying to grow this into an open source effort. And to that end, we are made to the top of Hacker News multiple times. We have a Discord community where a bunch of people are trying it, a good interaction on GitHub as well. So I would urge you all to go and try it out. And if it doesn't work, let me know. And if it works, do use it. And not just that, we have received a bunch of popular press and academic press internationally and domestically as well. And to demonstrate that this, people are actually using it, we have a hosted service that we run from our lab. And we have had more than 300,000 invocations in the last 2 months. All of this is just organic growth from word of mouth. So this is the effort that we have. It's called the Gorilla LLM. The code, the model, and everything is open source and Apache 2.0 license. So you could also use it commercially with no obligations. With that, I would like to conclude at a high level. To summarize, what we do is introduce this concept called retrieval-aware training that lets you train, being cognizant of the fact that retrievals aren't really accurate. And second, given the task that we have, it also gives us the benefit of putting an accurate number as to how much a model hallucinates. And by hallucination, I mean make something up. Thank you.
Okay, great. Thank you. We can take one question while the next speaker sets up.
How are you generating training data for this?
Yeah, great question. So this is a lot of this depends on just basically going ahead and scraping your APIs. And unlike a lot of licensing issues that people have run into, APIs are meant to be distributed. Like if I'm Stripe and I have a payment API, there's no incentive for me to hide it. I want to give you the API because when you use Stripe, I get paid. So APIs are meant to be distributed. So the incentives are very well aligned. And that's why you have people with tutorials, examples, Swagger files, etc. So we just scrape all of that. And then with self-instruct, we come up with the training data set to do that. All right, thank you very much. And I'll be around if you have any questions.
Our next speaker is Nayoung Lee, who will tell us about teaching arithmetic to small transformers.
Hello, I'm very pleased to introduce our recent work on teaching arithmetic to small transformer models. So this work is joint work with our wonderful collaborators, Kartik, Kangol, Jason, and Dimitris from University of Wisconsin-Madison and Princeton. To begin with, we are particularly interested in this emergent abilities that comes out when we train large language models with massive data. This is particularly interesting to me because these tasks were not specifically encoded in the training objective where we train the models on the next word prediction objective. So we've seen a lot of successful cases such as text generation of like Hemingway style text generations or many different tasks, but we find that the model is not specifically good at arithmetic tasks. For example, like Eugene gave us an example on Monday that it's not good at multiplication, but it's not even good at large number addition. So addition is kind of hard for the model, and we're interested in understanding how decoder models actually learn addition and whether this next word prediction objective from training the model from left to right on the text data is the most effective way to train addition. So prior research have worked on emergence properties with respect to the scales in terms of the model size and the data size. But untangling the factors that comes into play is very difficult because there's too much data and like the scale is too big. So what our solution is try to choose the simplest setting we can analyze on, which is addition, and we perform a lot of ablation studies. So we choose to teach the addition to a small nano GPT model, and our findings is that how we sample the data for our training data set and how we format the data is very important for the model to learn. So let me briefly give an introduction of our experimental setting. We use a nano GPT model, which is a very smaller version of the GPT models we use, and has only 10 million parameters. And the difference between the other model is that we specifically use a character level tokenizer, and we train the model from scratch, whereas most of the other works use a pre-trained GPT models. And the task is primarily on 3-digit addition, but we extend to other arithmetic tasks and extend the length we focus on. And the goal is to mostly evaluate the importance of sampling, formatting, and prompting. But in this talk, I'll mostly focus on the formatting aspect. So how does training happen to teach the models how to add? We just give a bunch of addition examples, and we train the model to output the most likely, the correct answer with a high probability. But sometimes it feels a bit weird to do this for an arithmetic task. So let's consider an n-digit addition setting. On the left, we have a conventional way of writing addition, and on the right, we have a way to simply flip the output so that there's on the left, on the conventional data, we output from the most significant digit to the least significant digit, and on the right, we reverse it so that the least significant digit comes first. So if we train the model on our conventional style, the model is now trained to output the most significant digit first. But this requires the model to find a mapping that has to use all 2n numbers that appear in both operands, because the carry-ons propagate from the least significant digit to the most significant digit. However, if we simply reverse the output, and so the trained data is now consisting of the reverse version of the addition, and we train the model to output in the reverse way. And if we do so, the model now only needs to find a mapping that maps just 2 digits of the corresponding digit position and the carry on to perform the addition correctly. So in other words, the model now needs to learn a simpler function with a reverse version of the output. So the result on the bottom shows that if we do so, if we train the model to output in a reverse way, it can go to a higher accuracy with much smaller number of training examples. So let's think about how we humans do addition. So we add by going from right to left, and we write out our carry on operations on the intermediate step, and we take it by doing step by step. So based on this, we can think about a chain of thought style data format, which we construct to use. Well, the chain of thought data format is actually taken from other papers, but we train the model from scratch to output in such way. And we observed that all the modified format, which is reverse and simplified scratchpad, detailed scratchpad, these methods all reach 100% accuracy at some point, but by giving much more information, the model is now required much less train examples to perform well. And this is because the train of thought style training data teaches the model to learn the easier, simpler task by doing it step by step. So, so I've been talking about how.
I'm sorry. Can I ask you? So, once you train it to output the sum in reverse order, what happens? Can you do further small amount of training to have it actually output the sum in the left to right?
Oh yeah, that's a very interesting viewpoint. So that was what I plan to do, work on later, because like that's what's desirable. We want the model to do it better left to right. And I think your question is if we train it on right to left first and then further train a little more on left to right, whether it helps. But I don't have a strict answer to it yet, but we do have a fine-tuning setup where we try to have this, we have this 3-digit addition trained from right to left, and then we further train it on 4-digit on left to right, but it didn't seem to help very much, but I think it's a very interesting direction to work on. So I've been talking about the data formats, but what's also interesting is that the model goes from not knowing any additions on a small number of examples to suddenly getting to fully understand how to do an addition. So why this happens is one question that appeared. So, and some relationship with a matrix completion gives some explanation to why this happens. So if we think about an addition chart on the left, where each elements are the sum of the row index and the column index, then this addition chart, filling up the addition chart would be, this addition chart itself is rank 2 matrix, and filling up this chart is performing the low rank matrix completion. And the matrix completion theories give us that if we reveal ON outputs, then it starts to be capable of completing the matrix perfectly. So this gives a partial explanation to why the model goes from not knowing addition to suddenly being able to add fully given enough data samples. But it's, sorry. I'm running out of time, so I'll briefly talk about while matrix completion, if you have this empty rows or columns and it's not able to complete the matrix, but our GPT models, even if we have exclude 500 numbers out of 1,000 three-digit numbers from anywhere appearing in the training examples, it's almost fully capable of adding the numbers that was hidden. And also if we hide like a number 5 appearing in the least significant digit anywhere in the data set, it's still capable of adding it because it can infer from 5 appearing in other digit positions. So that's one difference between matrix completion and our nano GPT models. And I'd also want to emphasize that the question whether the model is truly understanding addition. So unfortunately, our answer is that when we train the model on just 1 and 3 digits, but it doesn't have 2 or 4 digits, it's unable to perform 2-digit or 4-digit additions. And even if we train it on this detailed scratchpad data, it randomly starts dropping off a random digit and gets it wrong. So our answer is no. It's just learning a pseudo algorithm that of the C number of digits that maps to a correct answer. And there's many more in our paper regarding what happens for other arithmetic tasks, or what happens if there's text in our data, few-shot prompting, and so on. So if you're interested, please check our paper. And the key takeaways will be that data formatting and how you sample it is very important. And also, we can make some connections with the low-rank matrix completion to understand why the model suddenly is capable of learning addition. And also, lens generalization is still challenging. Thank you.
Thank you. We have time for a couple of questions.
Hi, I was sort of expecting you to see, given that you reversed the outputs, that you would have experimented with reversing the inputs as well.
Oh, yeah.
Did you try that?
Yes, that's right. And the result was almost the same. So, but in terms of our humans analyzing the output, we just use only the reverse output because it's like to process the result, we would have to, we humans have to revert it back.
Any other questions? Okay, if not, let's thank the speaker once again. Great. Our next speaker is Eric Wallace, who will tell us about memorization and large language models.
Awesome, thank you. Yeah, thanks everyone for sticking around for the final talk of the final day. Hopefully I can do it justice. What I'm going to try to do in this talk is convince you that large language models memorize pieces of text from their pre-training data. And the way I'll do that is I'll break this talk into 3 pieces. First, I'll define what I mean by memorization and how we can measure it. Second, I'll present an algorithm for how to actually extract memorized data from language models. And then third, I'll analyze kind of how well it works and where I see things going in the future. Okay, so first I'm going to define this term I call generation-based memorization. The idea here is very simple. We're going to have some pre-trained language model, like let's say this is GPT-3 or something like that. I'll assume for the purpose of this talk that it's completely a black box. I don't know what it's been trained on. I don't know what details it is. All I can do is put in some prompt and get some sample back from the model. And the goal here is we're going to put in some prefix of text, for example, something like, in this case, the very beginning of Harry Potter. And I'm just going to press go and just generate from the model and then see what comes out. In this case, what happens when you put this into GPT-3 is it'll regenerate verbatim the entire first page of Harry Potter, and it can keep going for a long time. And so broadly, what you can think of in these kind of cases is basically the model is so likely on this particular suffix that simple sort of like greedy decoding or generation from the model will cause you to regenerate this sample. So why is this good or bad? I kind of want to argue basically that memorization can both be simultaneously really, really good or really, really bad, depending on the context. And so, for instance, in cases like question answering, reading comprehension, things like this, people really love the fact that language models kind of soak up all this information from their pre-training data. And so people do a lot of evaluation of things like, you put in questions like, what is the 14th Amendment? What is differential privacy? What is the advantages of this over that? And they say, look, the model can do really great things by recalling exactly information from its training set. And so this is broadly seen as a positive. At the same time, if you put on sort of like a privacy hat for a second, you can also put in prompts like Eric's social security number is, generate from the model, and maybe if you have private information in your data set, it'll just perfectly regenerate verbatim information from the model. So obviously, if your data is private or sensitive, let's say, for example, you're training on health records, emails, chat logs, anything like this type of generation is going to be a catastrophic privacy leakage. Moreover, as we've seen sort of throughout the workshop, there's also a bunch of cases where like even if your data is private, there can be a lot of issues with models memorizing it. And so Pam on Wednesday talked about copyright data issues, which is a major problem in modern scale systems. We've also seen cases of, for example, like just nasty data that's out there on the web that we don't want models to memorize. For example, this is a case of a leaked medical study that was accidentally placed online. And also, a common thing that's shown up in the workshop throughout is basically, are these language models really just memorizing stuff from the web and using that to solve tasks, or are they doing novel reasoning? And so one thing you also don't want models to memorize is academic test data sets. So a lot of times the data sets that we use to evaluate models are accidentally placed online and being scraped by training sets. And so in all these cases, this is instances where even for public domain data or things that's just out there on the internet, we don't want models to memorize. So the takeaway here so far is basically that memorization can be good or bad. What I'll talk about next is basically a concrete algorithm for how to actually extract memorized data. So the setting here is I'm given some language model, let's say it's GPT-3, and I want to be able to interact with that model and then extract a list of examples that I think are from the training data. In general, how you can do this is actually quite simple. First, what you can just do is take the model and then just generate a ton of samples from it. So for instance, I take GPT-3, generate, let's say, 100 million samples from the model. And so now I have this massive pool of text. And then the main technical question becomes, how can I kind of sift through that big corpus, identify cases where I actually think it's from the training data? And so basically kind of flagging or finding samples that we think are training data. And so if you're familiar with privacy, this is the membership inference problem. This is given a piece of text. In this case, it's a big pool of samples. Is it from the training set or is it not? And so what I'll present next is basically concretely for language models, what does a state-of-the-art membership inference method look like and how do you run that in practice? The idea here is actually quite simple. Basically, what you can imagine is we put in a set of samples into the model. Let's say, for instance, Eric's social security number is and John Doe has cancer, and we get the likelihood that comes out from the model. The simplest baseline you could imagine for membership inference is just to say, okay, this sample is really high likelihood, and since language models overfit, or to some degree, their training set, the reason it's high likelihood is because it's from the training set. And so the simplest membership inference attack is just thresholding based off the model's likelihood or perplexity or something like that of the text. The issue with doing this is that things that are high likelihood could be from the training set, but they also could just be easy samples. So things that are just like generic, easy to language model text that's very basic English, that's also going to be high likelihood under the language model. And so what you want to do is kind of calibrate for the difficulty of a sample. The way you can do that very simply is by introducing just a second language model. I'll represent this as a white box because this is a language model we train ourselves, but I won't leverage any aspects of the fact that we know what the details are. In practice, we just download some model of Hugging Face and use something that's available. But you put the same set of samples through and then compare the likelihoods. So for example, this first sample, both models thought it was really high likelihood text. And so in this case, you'd probably think it's not from the training data, and instead it's just an easy sample. In this case, the target model assigned it a much higher likelihood than this reference model. And so I would predict that this sample is probably from the training data. And so basically what we do is we take that huge pool of samples, let's say it's 100 million samples, we filter or sort them by this kind of ratio between this target model and this reference model's likelihood. And then we just inspect these kind of high scoring samples under that on the metric. And hopefully those are instances of kind of like privacy leakage or copyright infringement. In practice, what ends up happening, which I'll show on the next slide, is basically because language models don't overfit much at all. I think in Sasha's talk on Tuesday, he talked about the fact that we just do like one epoch of training. And a consequence of that is that really the train test gap is really small. And so in practice, when you run these kind of membership inference metrics, what happens is that it's actually really hard to identify a lot of memorized content. Instead, what you end up finding is kind of a really high precision, but extremely low recall classifier. So we can reliably identify a very, very small set of samples. But for that set of samples, we have high confidence that they're from the training set. Concretely, here's a couple examples of what you can get. So we've applied this to a couple different models. This is an instance of GPT-3 where you can, as I showed on kind of the first slide, you can get it to regenerate, for instance, entire chapters of Harry Potter. In the case of a model like Codex or GitHub Copilot, which is an open source, or not open source, but proprietary code assistant model, you can get it to generate things like non-permissively licensed functions or entire code files. Interestingly, you can also apply this exact same methodology with just slightly different details to, for example, image generation. In this case, this is running Stable Diffusion, where on the top here, I'm showing a series of images that are from the model's training set. And on the bottom, I'm showing a series of images that have been generated by the model at test time and then scored with our membership inference metric. And you can see also in the case of images, you can get kind of this like sort of verbatim generation from the model. Finally, you also get kind of like privacy type infringement with these kind of models as well, where you can prompt the model to, for example, regenerate an image that's very similar to a training image of a particular individual. So these are kind of qualitative results on both language models and on image models. To conclude in the last maybe like 5 minutes of my talk, I just want to give kind of a perspective on why this is happening and where I see things going as models kind of continue to scale and develop. One major point I want to get across is that as we start to scale models up, so for example, going from the, let's say, small language model era to the large language model era, the amount of memorization has increased by huge amounts. So concretely, what I'm showing in this plot, for instance, is just on the x-axis here, I'm scaling up the amount of model parameters in my language model. On the y-axis, I'm plotting some metric of memorization. I won't get into the details of exactly what it's plotting, but the takeaway here being that simply scaling up models, which improves accuracy, improves results overall, will simultaneously cause, for example, privacy leakage to increase by a similar amount. And so I think the takeaway that you can get from this is basically that as we continue to keep performing scaling, whether it be with new hardware, data, et cetera, you can imagine that these kind of memorization issues become exacerbated over time. If you think about this from the question answering perspective, it's kind of the opposite story, which is, hey, if we just sit and wait and watch the scaling people kind of do their thing, question answering will get a lot better. But if you think about it from a privacy perspective, it's mainly, things are getting worse over time. The same kind of story applies when we think about the data. And so, for instance, one thing we've looked at a lot is that, okay, well, a big language model pre-training data set is pretty heterogeneous. It's kind of a mix of a bunch of different sources. And one thing that you often come across is that there's actually samples that are duplicated a bunch of times. So for instance, maybe there's quotes out there that have been mentioned a bunch. Maybe there's news articles that mention the same kind of topic a lot. And one thing we found is that having just a few duplicates in your data can cause massive amounts of increases in memorization. So for instance, what I'm showing here is basically on the x-axis, I'm plotting for a particular n-gram, how many times does it show up in the data? So for instance, over here are cases where an n-gram is a singleton, it's unique in the data. Over here are cases when an n-gram shows up on the order of 100 times. And interestingly, what you see is on the y-axis here, I'm plotting a metric for generation-based memorization. Just increasing the number of duplicates by a factor of, for example, 100 could increase your amount of generation-based memorization by a factor of, let's say, 10,000 or 100,000. And so it kind of has this super linear effect where just having a piece of text duplicated, let's say, 10 or 100 times could cause this kind of huge amount of increase in privacy leakage. The good news from this is that if we just deduplicate the data and be very careful with how we collect things, you can really drastically reduce the amount of privacy leakage in practice. The bad news from this is if you care about, for example, question answering, that means models are going to be really, really bad on these kind of like rare questions. So if you ask about esoteric knowledge, models are going to be awful. If you ask about common stuff, they're going to be like disproportionately good on this kind of examples. And so this paper here is talking about this idea of like from the privacy perspective, if you deduplicate. This paper here is talking about from kind of the question answering perspective, what happens when you are evaluating on these kind of like esoteric long-tail knowledge questions. The last thing I want to mention is mainly a shout out to a paper that we just put on arXiv like 2 days ago. The core idea here is basically, could we kind of decouple the sort of like knowledge aspect of the model and the base language model itself? And so the idea here, which we're calling like siloing your legal risk, is basically to say, okay, what if we collect a data set of only public domain, low risk data? So this could be like open source code, old books, things like that. we're going to use that data only to fit our language model. And then we're going to put all the nasty high-risk data, for example, copyright stuff, private things like that, into a large database that models can retrieve over and read at test time. And so, for instance, maybe they have some copyright news articles in there, and we're not actually using those to fit the model parameters, but instead it can retrieve at test time, read those documents, and then use that to update its predictions. And so kind of these two sources are merged only at test time, not during training time. And so what this lets you do is you can easily attribute like which documents is my model using for its prediction by just looking at which things it's retrieving over. It allows you to easily delete or add data. If you're, for example, someone's unhappy with their data being included, it's easy to opt out. If people want to be compensated or attributed for their data being used in a model prediction, it's easy to get that out of the retrieval engine. And at the end of the day, all the the nasty, complicated machine learning stuff is only happening on kind of this public domain data, which we're ostensibly just free to do with that, whatever we can with it anyway. Okay, these are the main things I want to say, just to kind of summarize what we talked about so far. Basically, the idea is that language models do memorize text. This is good in the case of question answering. This is bad in the case of privacy or copyright. And especially as we start to scale up models and they get more powerful, this issue is often exacerbated. Second, as I kind of pointed out in the beginning, and as we've seen actually throughout the workshop, it's been definitely a recurring theme, is that whether it be privacy, legal, ethical, whatever perspective you're looking at, that can be a huge important aspect of the data that you're using to train and kind of build machine learning systems. And finally, which I think is kind of the key new thing in this talk, is that there's really this kind of trade-off that exists between accuracy and privacy in many cases. For a lot of applications, we care about models memorizing and absorbing as much as they can from the training data. From the privacy perspective, you want to memorize and remember as little as you can from the training data. And so how do you kind of balance and modulate those things in practice, whether it be new algorithms or kind of new sort of model designs, as we showed in the silo example. Cool. That's everything. Thank you.
Thank you. We have time for 1 or 2 questions.
I can probably just shove this out faster than I could shout. So how much does this happen when you increase the temperature? Was this like you reproduce Harry Potter at temperature 0, or is that, can you raise the temperature and have it do that as well?
Yeah, generally for memorization examples, you want to decode the highest likelihood completions from the prompt. And so I think what gets tricky is like if you can't control how sampling is done, that makes it harder to extract memorization. And so in all these cases, like we assume we're doing either like greedy decoding or even like beam search decoding or some sort of like depth first search to find the highest likelihood sequence.
Oh yeah. If you train for like multiple epochs, do you think that would have a similar effect to duplicate data?
Yeah. We actually looked at that in the paper on deduplication. I think it's basically, you could think of it like doubling the data the second you do the second epoch. And so similarly, kind of the same story, which is like doing multiple epochs will help your question answering performance a lot, but then hurt your privacy by a big factor as well.
Any other questions? If not, let's thank Eric once again. And we actually have one last speaker, Anil. Okay, great. So our final speaker is Anil Ananthaswamy, who will tell us about ChatGPT and theory of mind.
So thank you very much. This was a very surprise thing. We just decided on this 40 minutes ago. So Eric's was the final talk. This is the final talk. And we're dead certain there's no more. I just wanted to tell you a little bit about a very intriguing ability that LLMs have, especially the final versions now that we're seeing, because I think it really is a property that brings to mind these questions that we've been asking. Are these LLMs capable of reasoning, and are they stochastic parrots, and these kinds of issues? So One of the things that you can do with these LLMs is to see if they have some property called a theory of mind. Now, theory of mind, maybe you're familiar with what this is, or maybe not, but let me just tell you what this uh, ability is. It's an ability that all of us have to be able to infer what is happening in someone else's mind. So if you are looking at someone and taking behavioral cues by seeing their face or their, the way they're behaving, you kind of can infer what they might be thinking. So you have a theory about what is happening in their mind. So that ability, like if I'm looking at someone while I'm speaking and they're making a face that seems to indicate that they're not understanding what I'm saying, I can infer basically that they're not understanding what I'm saying, right? There's a very simple test that was designed a while ago, I think probably 1980s, called the Sally-Ann test. And so here's the setup. So you have a room where Sally and Anne are in the room together. They each have a basket with lids. So Sally hides a marble in her basket, closes the lid, and leaves the room. And then when Sally is outside the room, Anne takes the marble from Sally's basket and moves it into her basket and closes the lids. So basically, from the outside, you can't tell where the marble is. Now, Sally comes back into the room again, and this scenario is being played out, let's say, to children, and children are being asked now, where will Sally look for the marble? Now, depending on how old the child is, the child might say Sally will look for the marble in, Anne's basket, because the child knows, because the child has been looking at this scenario playing out, and the child knows that the marble is in Anne's basket, and the child will say, oh, I know that the marble is in Anne's basket, so Sally will also look for the marble in that basket. But there's a stage in the development of the child where the child will say, actually, I know that the marble is in Anne's basket, but Sally doesn't know that. So Sally will actually look for the marble where she left it. And hence, this is showing that the child now has the ability to model not just what's happening in its mind, but also what's happening in Sally's mind. So this ability now that has developed in the child is the ability that's called theory of mind. Now, I have been writing a lot about this issue as a journalist, and also it's something that I think about a fair bit in the sense of, the models of the self that develop in nervous systems, and how nervous systems model, the body and the outside world, and how nervous systems model what's happening in other nervous systems. So the question that came up was, how much of this ability now exists in these large LLMs, right? So the problem with trying to query an LLM like ChatGPT is, of course, it's probably seen a lot of these examples in the literature. So really the problem is one of trying to come up with ways of phrasing this question and hoping that it hasn't seen that particular version of the question. So here's a question that I asked ChatGPT. Alice and Bob are in a room together. There's a table with two drawers. Alice takes off her reading glasses and keeps them in the left side drawer. If Alice wears the wrong glasses and reads, then she gets a severe headache the next day. Keep this in mind. So I'm telling ChatGPT this. I'm not sure why I added keep this in mind, but this was just one of those things you do with the LLMs these days. The question continues. Now Alice leaves the room. When she's outside, Bob removes her glasses and puts them in the right side drawer. In the left side drawer, he puts a pair of glasses that look exactly like Alice's but have the wrong power. He closes both drawers so that there's no way to tell that he switched Alice's glasses. Alice then comes back, takes her glasses, and starts reading. How will she feel the next day? Think carefully and answer. This is the query for ChatGPT, right? So here, the attempt is to kind of introduce multiple layers of indirection so that in the hope that the LLM hasn't seen this in the training corpus, right? And how many of you think that ChatGPT would have answered this? Michael says yes. Told you something, so Steven says yes. Okay, this is ChatGPT's answer. Since Bob switched Alice's reading glasses with a pair that looks identical, but has the wrong power, Alice will unknowingly use the incorrect glasses when she starts reading. As mentioned, if Alice wears the wrong glasses and reads, she gets a severe headache the next day. Therefore, Alice will have a severe headache the next day as a result of using the wrong glasses. Right? And I want you to notice the word that I have italicized and underlined. That's me doing it just for highlighting it. But that word is indicative of someone else's state of mind. Unknowingly, it's kind of showing the language is suggesting that there is an inference about what's happening in Alice's mind. But I decided to query further. I asked, why will Alice unknowingly use the incorrect glasses? And again, this is pretty amazing. Alice will unknowingly use the incorrect glasses because Bob switched her reading glasses with another pair that looks exactly like hers but has the wrong power. When Alice returns to the room, she is not aware of the switch and assumes that the glasses she picks up from the left side drawer are her own. Since both pairs of glasses look identical, she has no way of realizing that the glasses she's using are not the ones she initially placed in the drawer. As a result, she uses the incorrect glasses without knowing it. Again, look at the underlined italicized words. Those are all words that refer to an ability to model the content of another agent, in this case, Alice, right? Now, for me, I mean, we all had this debate over the last 5 days as to whether LLMs are stochastic parrots or whether they're capable of reasoning or are they generating novel outputs, etc. But when you're confronted with outputs like this, right, it really is very, very difficult to argue that all they're doing is parroting something that they've seen. I mean, I've tried very hard to come up with queries in the hope that these are queries that ChatGPT wouldn't have seen, and it more often than not gets it right. And I have to caution you that the same query given to ChatGPT a month later, it got one sort of crucial bit of information wrong, and as a result, the whole answer kind of falls apart. So it's still not perfect, but the fact that it's doing this, at least for me, raises questions about what exactly is happening inside these models. So I just want to leave you with that. I don't have an answer as to what's happening inside these models. I think one of the things we learned over the last 5 days is really we're all kind of trying to figure it out, and the theoreticians are working really hard to answer those questions. The empiricists are playing around with it and trying to come up with ways of testing these things. But this is where things are going. You can imagine LLM being the kind of thing that is used to provide some sort of brains to a robotic setup. And this already to me tells you that you can have an agent, an LLM-based agent that is capable of somehow modeling the states of minds of other agents, right? By if it can examine the scene outside and learn from that and then be able to infer something. So I just want to leave it there as a way of ending this whole workshop. So thank you very much. It's been a pleasure to be here for 5 days, listening to everyone. So thank you.
Great. Thank you so much for sharing your perspective. We have time for some questions.
Oh, yeah. So could you go back to your prompt? Actually, there's a part in there that I wanted to address. Yeah. Well, you're telling you.
Oh.
You have a couple parts to your prompt, actually. Yeah.
This one, yeah.
Right. So when you instruct the operation to basically assume that she takes her glasses.
Yeah.
Why does ChatGPT 4 not understand that she finds her glasses correctly anyway?
Why would it assume that?
Well, you tell her that she does it. So like she finds her glasses. Who cares how?
Well, the assumption here is that Alice will look for her glasses where she left it.
Yeah, but you don't. But you asked about her glasses. No, not where she thinks she left them. I'm just sort of curious about like.
I think if we change that prompt to just say where she thinks she left, yeah, it's worth trying all those variations. This is the prompt that I put, but you're right. I think that all of those are cues to the LLM to go somewhere, in its search space, and I think those could be enough for it to generate the answer. It's giving it enough of a hint to produce the answer that looks like reasoning. And I think that is in a sense the question: is it really reasoning? I don't think at this point we can definitely say that at all. That it's reasoning. It could just be that there's enough hint. There's enough of a hint there in the question, in the query, that it just autocompletion is enough to get something that looks like a reasoned answer. Yeah.
Other questions?
Yeah, I'll just say something. So just following up on that point, I would see the prompt as actually making it harder for GPT.
Why do you say that?
Well, in the sense that it says Alice comes back, takes her glasses. Now, you'd have to be thinking colloquially to say, well, Alice came back and took what she thought were her glasses. It doesn't say it's, it would be easy to get confused and say, look, literally, if you were...
It's ambiguous.
Yeah, if you were taking it literally, you would say, well, Alice came back, took her glasses, and therefore there would be no problem. But somebody who is more human would think, okay, she came back and took what she thought was you'd be looking even more from her point of view to say, well, she came back, took her glasses, but that's what she was thinking, not what were her glasses.
I mean, I would agree with both of you. And I think therein lies the problem, that I think we are trying to kind of put ourselves inside GPT's head and trying to figure out what it's doing. And we haven't a clue really at this point. But there is enough ambiguity here that you can attribute some ability to GPT. By the way, this is, I think Eric was talking about it, or, this is an emergent property, so to say, emergent only in the sense that this wasn't there in GPT-2 and, GPT-3, 3.5 onwards, you start seeing this ability more and more. So scale matters, size matters. But I personally have tested this ability with all sorts of queries, and it's quite intriguing that it does get much of these things right, but also it gets it wrong. And when it gets it wrong, it's very instructive, because that's the thing that's telling you that, okay, this is not quite reasoning yet. That it's it's sort of doing very sophisticated pattern matching, and by and large, it gets it right and it looks like reasoning. But then when it fails, it's so obvious that it's not a reasoned answer.
I suppose one thing I'm curious about is, if you ask in the context of your talk, you ask a human to talk about this, it's quite evidently the Sally-Ann test, right?
Yeah.
It's, and so I'm so curious whether, in some sense, ChatGPT is recognizing it as the Sally-Ann test.
Sorry, I didn't understand the
I'm
question.
curious whether, in some sense, ChatGPT is recognizing a sort of homologue of the Sally-Ann test.
I'm pretty sure it is. Yeah,
extrapolating
completely. And I think the challenge for us as people testing this would be to come up with ways of asking these questions without, I haven't yet figured out how to ask this question without the Sally-Ann template. All I did was change Alice and Bob, and that's trivial. So I'm pretty sure that it has seen enough Sally-Ann test examples that it's, that's the metaphor it's working with.
Right, but so this might then be an interesting avenue to start constructing tests of theory of mind that don't involve putting objects in containers. And
I have done that. I was telling Stephen that when those Russian dolls, which have dolls within dolls, Matrushka dolls, I think. So one of the questions I had constructed was, Sally and Anne are both looking at a series of nested dolls. They both look. So Sally is putting it together. Anne is watching her. And then Anne goes out of the room, and while Anne is out of the room, Sally then takes it apart, takes the innermost one out, and puts it back. And then Anne comes back in, and the question is, how many dolls does Anne think? So you can't keep constructing this, but ideally you want to get away from the Sally-Ann, which I haven't yet done. So I don't know the answer to that, but I really would like to come up with queries where we move away from that template and see if it works. My suspicion is that it will probably work to an extent. Yeah, thank you very much.
Okay, well, thanks